So far we have studied the first order systems. And also we have seen a special example of the second order systems. Okay, and that is our preparations. So for the first order system, if you remember that time we talked about the first order system response to a unit step input response and unit impulse response, unit step response. Let me do the graph. Okay. So basically here we know say unit impulse, and also we have the unit step input, and also we know the unit ramp input. Okay, so we have studied the three cases. And for the second order systems in particular, we have studied is the unit system response. Okay, so basically the curve simply something like this. Okay, so for this curve, it's something like this. For this curve, something like this. And those things we've seen before. Okay, so you can go back to to find out your lecture notes for individual details. For the higher order systems, and that means the system's degree is greater than 3. Okay, and for those cases, basically here we can only do qualitative introductions for this. So in general, for higher order systems, is transfer functions. And let me describe it in very general way. C as over R as will be equal to A n. Okay, so here you can see I begin to write down a very generic form. And here usually we assume m is less than or equal to n. And most of the time it's less than n. And for practical systems, okay. So given these systems, and for the higher order systems, the first step is to factorize. Okay, and try your best. Here I can only say try your best and factorize the transfer function. Hopefully that can be converted into the summations of something like this. Okay, and sometimes it may not be so simple. It also might have combination of the second order systems. And could be like this form, or could be the numerator could be the different. But I just want to emphasize the factorizations. Hopefully, we can factorize into what we know. For this one, basically, this is going to in the time domain. Let me convert into this. I think I forgot one thing. For say examples, unit step input, and that means RT equal to 1, or which means RS equal to 1 over S. Okay. So, for example, for this case, then we can know CS basically equal to the whole things, the transfer function multiplied with RS, right? So, factorize the transfer functions, factorize, I think not the transfer functions, factorize the CS, and which is equal to the transfer functions multiplied with RS. Okay, so that's what I mean. So basically this is CS. Okay, we want to determine the output. So basically here, hopefully we factorize the things onto the basis we have known. Basically this one corresponding is a constant term. This one corresponding is our first order systems. And factorize to this form basically is to fit into our knowledge of the second order systems. So we do nothing more but just try our best to hopefully we can factorize and build it into the template we have known well already. Okay, so that's the key. And how can we try our best? And usually the software like the MATLAB will help us and to factorize the things. But most of the time for control system, if the degree is higher than 3 or 4, and that one always we can use engineering intuitions to approximate beforehand already. Okay, so you don't need to be so scared, and usually the degree won't be so high. Okay, because we already should have some way before this step we can simplify the system already. Okay, but here we talk about the theory here. So with those informations, basically the first thing is from here for the first order system, you can tell by the position of the pole. And again here we come to the review. For this system, if the PI is here, and compared to the PI is here, its time response corresponding is this. So this is the So for this case, the system response will be decaying that fast. Corresponding to the pole here, the system response will be decaying faster. Okay, so here we can do the only schematic. And for this case, and again, we fit into our the previous information. Basically, this is a second order system. It has complex conjugate poles and a pair. So for example, here and here. Okay, and depends on the locations, and which means this one is determined by, this one is the real part from here to here. Okay, so that is the, so this is minus theta omega n, for example. And this one is omega n times 1 minus theta squared. So really depends on the two values. So you can determine, this one basically determine how fast, just like this, how fast that would decay. This value determines how fast it is oscillating. Okay, so basically by here we can always and do a very good approximation. And from here you might try is this. For example, if system will combine with slow and fast dynamics, and in terms of the engineering, and very good exercise is this. Under certain approximations, you can simply ignore the fast dynamics. Why I can say so? Because the system's behavior is at majority determined by the components of a slowest dynamic component, right? You know what I'm saying? If a police a group of police car chasing a group of gangs, they always try to catch up the slowest one because they can get one and they will get a string of the things. They will try to make sure they catch up the one. So they always catch the slowest one, right? The similar concept. Eventually, because the fast dynamics will behave very quickly, so basically its influence to the system dynamics will be very short. So we want to study system dynamics, and the major dynamics of the system, basically that is governed by the slowest one. Okay, so here for this example here, if you like, you can choose either this in terms of first order system, and if we have, for this case, if we have other reports, basically here you like to choose the one that has give you the slowest the decay performance. Okay, and by saying so, I'm going to we can get ready to jump into the new sections. And the new section basically pertaining to these discussions. Scott probably can go to the next new section.